Chapter 1. Before Clocks. The Sky as the First Timekeeper. Long before there were clocks in towers, watches in pockets, or quiet numbers glowing on small glass screens, time was known by looking outward. It was known by the pale widening of dawn over grassland and shore. It was known by the slow dimming of evening, when birds settled into branches and the world grew softer at its edges. It was known by warmth returning after cold, by fruit ripening on trees, by animals moving across open ground, and by the moon changing shape night after night above the darkened earth. The first timekeepers were not made by human hands. They were the great repeating patterns of the natural world. Day followed night. Night followed day. The sun rose, crossed the sky, and lowered again. Its light gave shape to waking work, to travel, to gathering food, to sheltering, and to stories told in the cooler air. Even without names for hours, people could feel the day unfolding. Morning had its own character, bright and fresh. Midday carried heat and brightness. Evening brought lengthening shadows, returning animals, and the gentle closing of flowers. This kind of time was not counted in minutes. It was noticed. A cycle is a pattern that repeats, and the world offered many cycles to careful eyes. The moon gave one of the clearest. At first, it might appear as a thin silver curve, low in the twilight. Then, over many evenings, it grew rounder and brighter, until it became full, lighting paths, water, leaves, and stone. After that, it slowly thinned again, returning toward darkness. From one new moon to the next is about 29.5 days. This is called a lunar cycle, because lunar means relating to the moon. For people living close to the land and sky, such a cycle could be useful in many ways. The moon's light might help guide travel at night. Its repeating phases could help communities remember when to gather, when to begin a shared task, or when a season was turning. Some ancient markings found on bones or stones may have been counts of moon phases, though such evidence is often difficult to interpret with certainty. A row of marks can suggest careful observation, but it does not always tell us exactly what its maker intended. So we speak gently about these early traces. We do not need to imagine them as simple. Watching the sky without writing, without metal instruments, and without fixed calendars could still be a careful and thoughtful art. It required memory, patience, and the steady attention of many generations. Beyond the moon, there were the seasons. The year is connected to Earth's journey around the sun, though ancient people did not need to describe it in that way to understand its pattern. They saw the sun take a higher path in some parts of the year, and a lower path in others. They knew the smell of thawing ground, the return of insects, the first green shoots, the heavy seed heads of late summer, the falling leaves, and the quiet of winter. Solar means relating to the sun, and solar time was written across the world, in light and warmth. The sun did not rise in exactly the same place on the horizon every day. Over the year, its rising and setting points shifted gradually, like a slow breath along the edge of the land. To notice this was to begin to know the year, not as a number, but as a living circle. In coastal places, the tides also marked time. The sea moved in and out along the shore, covering stones and revealing them again. Pools filled, then emptied. Seaweed lifted and settled. Boats could be drawn up or set afloat according to the water's height. To those who lived beside the ocean, the tide might have seemed like another kind of breathing, linked in part to the moon, steady enough to be trusted, yet always moving. Plants and animals were timekeepers too. Certain flowers opened in one season and vanished in another. Trees budded, leafed, fruited, and rested. Birds migrated across wide distances, returning when the air and food were right. Fish appeared in rivers or along coasts at expected times. Herds followed grazing. Insects hummed in warm months and disappeared in cold ones. To notice these changes was not only practical, it could also be meaningful. The return of a star, the first call of a bird, the swelling of a river, the full moon above a gathering place, such things could belong to food, travel, memory, and ritual all at once. At night, when the sun was gone, the sky offered another vast pattern. Stars appeared one by one, then in multitudes. People in many cultures learned the constellations, the recognizable groups of stars that rose and set with the seasons. Some stars were seen only at certain times of year. Their return could signal that a season was near. In ancient Egypt, one star became especially important: Sirius, the bright star associated with the coming of the Nile flood season. Its heliacal rising was watched with care. Heliacal rising means the first time a star becomes visible just before sunrise, after being hidden for a while in the sun's glare. Imagine the eastern horizon before dawn, still cool and dim, and then a bright point of light appearing briefly before the sun washed the sky with gold. Such a moment could carry great meaning, because the Nile's flooding helped renew the fields with water and rich soil. Across the world, people looked upward and outward in this way. They did not all divide time alike. They did not all begin the year in the same season, or give the same importance to the same moon, star, tide, or harvest. But they shared the human gift of noticing repetition. They saw that the world returned to itself, not exactly the same, but in patterns gentle enough to be remembered. Before clocks, time was not separate from life. It was the path of light across the ground. It was the coolness before sunrise. It was the ripening berry, the migrating bird, the swelling river, and the tide sliding over sand. It was the moon growing full above a quiet camp, and the stars turning slowly overhead. And as people watched the heavens, they also began to watch the earth beneath the heavens. They saw that when the sun moved, shadows moved with it. A tree, a stone, a standing figure at midday, all cast signs upon the ground. Morning shadows stretched one way. Evening shadows stretched another. Slowly, gently, beneath the open sky, the first broad awareness of time began to gather around light and shade. Chapter 2. Stones, Shadows, and the Sun. Long before the sound of clockwork, there was the quiet movement of shadow. It happened slowly, so slowly that no one needed to hurry to see it. In the morning, when the sun lifted over the edge of the world, a tree, a standing stone, or a simple post would cast a long shadow across the ground. By midday, that shadow would shorten and draw close. Later, as the sun leaned westward, the shadow would lengthen again, reaching softly in the opposite direction. To notice this was to begin reading the day. A vertical stick or pillar used in this way is called a gnomon. The word may sound old and unusual, but the idea is simple. A gnomon is the part that casts a shadow. It may be a stick set upright in earth, a stone standing in a courtyard, or the raised edge of a carefully made sundial. As sunlight falls upon it, the gnomon's shadow changes. The shadow's length and direction tell something about where the sun is in the sky. At first, such watching may have been informal. A person might know that when the shadow of a doorway reached a certain stone, it was time to bring animals in from pasture. When the shade of a tree moved away from a patch of ground, it might be time to work there, or to rest from the warmth. No numbers were needed. The days spoke in light and shade. Over many generations, observation became more careful. Lines could be marked on stone, or scratched into packed earth. A post could be placed in the same spot day after day. People could compare one morning with another, one season with the next. Slowly, a simple instrument emerged: the sundial. A sundial uses the sun's shadow to show time when the sun is visible. It does not tick or ring. It does not move by itself. It waits beneath the sky. The sun moves, the shadow follows, the marked surface receives the passing light. In ancient Egypt, where sunlight was strong and the clear sky often wide, people used shadow clocks and tall stone monuments for solar observation. Obelisks, those tapering stone pillars rising toward the sun, cast shadows that could help mark parts of the day and reveal changes through the year. They were not merely practical objects. Like many ancient structures, they belonged also to worlds of ceremony, authority, and sacred meaning. Yet they show how closely people watched the sun, and how naturally stone and shadow could become part of timekeeping. Imagine an Egyptian courtyard in the cool of morning. The stone underfoot still holds a little of the night's softness. A shadow stretches long and blue-gray from a raised edge or pillar. As the hours pass, the light grows warmer. The shadow draws inward, then slowly turns. No one needs to see the sun move directly. Its path is written on the ground. Sundials spread widely in the ancient Mediterranean world. Greek and Roman societies used them in public places, in gardens, in baths, and in private homes. Some were simple, others were shaped with mathematical care. In a town square, a sundial could offer a shared sense of the day's progress. In a villa courtyard, it might mark the quieter rhythm of meals, visits, reading, or rest. Yet sundials also remind us that time was once much more local than it is now. A sundial shows local solar time, meaning time based on the sun's position in one particular place. Noon, by the sun, is when the sun reaches its highest point in that local sky. A town farther east or west would experience that moment a little earlier or later. Today, many regions share standard time across large areas, but sundials belong to the place where they stand. They keep the time of their own sunlight. This local quality gives them a certain gentleness. A sundial in one garden does not command another garden many miles away. The sun also helped people mark not only the hours of a day, but the turning of the year. Across the world, ancient builders sometimes placed stones, passages, or structures in relation to important solar events. These were not clocks in the modern sense. They did not divide every hour or minute. Their meanings could be practical, ceremonial, symbolic, or all of these together. In some cases, scholars can see clear alignments. In others, the exact purpose is still discussed with care. One of the best-known ancient sites is Stonehenge, in Britain. Its great stones stand on a plain where sky and land meet in a wide circle. Stonehenge is aligned with directions connected to the solstices. A solstice is one of two turning points in the sun's yearly path, linked with the longest and shortest days. At Stonehenge, the arrangement relates to the direction of midsummer sunrise and midwinter sunset. For the people who gathered there long ago, these solar moments may have carried deep seasonal and ritual meaning. In Ireland, Newgrange offers another remarkable example. This ancient passage tomb is famous for the way sunrise enters it at the winter solstice. Around the shortest days of the year, morning light can travel through a special opening and reach into the inner chamber. For a brief time, the darkness inside is touched by the returning sun. The event is quiet to imagine: cold air outside, pale dawn at the horizon, stone walls waiting, and then a narrow beam of light moving inward. Such places show patient attention. They remind us that the sky was not distant from daily life. It was a guide, a calendar, and often a source of meaning. The sun's rising and setting, its high summer arc and low winter path, could shape gathering times, planting seasons, ceremonies, and memory. There is humility in studying these ancient alignments. Modern observers may measure angles and dates, but the full thoughts of the builders are not always recoverable. A monument may have watched the sun, honored ancestors, gathered communities, marked seasons, or expressed beliefs that cannot be reduced to a single purpose. Timekeeping in these early forms was woven into life rather than separated from it. Still, the basic lesson of shadow remained beautifully clear. Light falls, a shape interrupts it, a dark line appears. As Earth turns beneath the sun, that line moves. From this movement, people found order. By afternoon, the stones of a courtyard grow warm. Dust glows in the slanting light. The gnomon's shadow lengthens again, pointing toward evening. Lines carved in stone become less distinct as the sun lowers. Birds settle along roof edges. The gold of the day softens, and when the sun finally slips away, the shadow clock falls silent. Then another question gently arises. How might time be measured indoors, beneath a roof, or after darkness has covered the land? How might the hours pass when the sun is hidden by cloud, or when night fills the courtyard, and the stones hold only the memory of warmth? In time, people would listen for another kind of measure. Not the movement of shadow, but the quiet fall of water, drop by drop, in the cool rooms of the ancient world. Chapter 3: Water Clocks in the Ancient World. When the sun was bright, a shadow could speak quietly across stone. It could stretch, shorten, and turn, giving shape to the passing day. But the sun was not always visible. Clouds gathered, rooms lay in shade, night arrived, and courtyards grew still. In those darker or enclosed places, people looked for another gentle measure. They found one in water. A water clock is often called a clepsydra, a word from Greek roots meaning water thief. It is a poetic name, as though time were being carried away drop by drop. Yet the idea was simple and practical. A vessel could be filled with water, and the water could be allowed to drip slowly out through a small opening. Marks on the inside of the vessel showed how much time had passed, as the level fell. In another form, water dripped into a container, and the rising surface reached one mark, then another. Either way, time was measured by flow. Imagine a quiet room with a clay bowl, a bronze vessel, or a stone container set carefully in place. The water glimmers faintly. A small opening lets a drop gather, pause, and fall. Then another drop follows. The sound is soft, regular, and patient. It does not depend on sunlight. It can continue through the evening, under a roof, or beside a lamp, when shadows no longer serve. Water clocks were never all alike. Some were very simple: a bowl with a hole, a marked jar, a measured amount of water. Others became more elaborate, with floats, channels, gears, or figures that moved as the water rose. But at the heart of them was the same calm principle. If water can be made to move at a controlled pace, then its movement can help people count a portion of time. In ancient Egypt, water clocks were used alongside shadow clocks and other forms of observation. One well-known Egyptian example comes from Karnak and dates to the reign of Amenhotep III, around the 14th century BCE. It was made for a world that watched the heavens closely, a world of temple ritual, seasonal change, and careful record-keeping. Its markings helped divide the night, when the sun could not cast its guiding shadow. There is something peaceful in thinking of such a vessel in a temple chamber. Outside, the stars slowly crossed the sky. Inside, water descended by small degrees. A watcher could look at the level and know that one part of the night had passed, then another. The clock did not hurry. It simply allowed time to become visible in a different way. Water clocks also appeared in Mesopotamia, where scribes and astronomers studied cycles of the moon, planets, and stars. In lands of rivers, canals, and cultivated fields, water was already a source of life and order. To use it as a measure of time was a natural extension of its place in daily experience. A steady flow could help mark intervals for work, ritual, or observation. Water clocks became useful in civic life. The word clepsydra itself comes to us through Greek, and in Greek courts and assemblies, such clocks could be used to time speeches. When someone spoke before a court, the water might be allowed to run for a measured span. When it was gone, the allotted time was over. In this way, flowing water helped bring fairness and order to public speaking, giving each person a share of the day. One may picture the scene without haste. Citizens gathered, voices rising and falling, a vessel set nearby, water slipping downward in a thin stream. The clock was not precise in the way later clocks would be, but it offered a common measure. It made an interval something everyone could see. In India, too, water timekeepers were known, and they appeared in different forms across the long history of South Asian astronomy, ritual, and daily practice. Some used floating bowls that slowly filled and sank. Others depended on marked vessels and measured flow. As in other regions, these devices belonged to a wider culture of watching the heavens, arranging calendars, and finding harmony between earthly activity and celestial cycles. In China, water clocks developed along especially intricate paths. Simple water clocks were known early, and over the centuries, makers created increasingly complex systems. Water could turn wheels, raise floats, and set parts of a mechanism into motion. Here, a mechanism means several parts working together to make something move. Some Chinese water clocks were connected with astronomy, the study of the sun, moon, stars, and planets. One of the most remarkable examples came much later, in the 11th century, when Su Song, a Chinese official and scholar, oversaw the construction of an astronomical clock tower. It used water power and complex mechanisms to display celestial information. An astronomical clock is a clock that shows not only time, but also movements or positions of heavenly bodies. Su Song's tower belonged to a long tradition of careful observation and skilled craft. It reminds us that water clocks could be more than dripping bowls. In some hands, they became moving models of the sky. Still, water itself is a delicate timekeeper. Its flow is affected by many things. If the water is warmer or colder, it may behave a little differently. If the pressure changes as the level in the vessel falls, the flow may speed or slow. A tiny opening may clog. The shape of the container matters. For this reason, water clocks were not perfectly steady. They required attention, adjustment, and understanding. But perfection was not the point. Each kind of timekeeper answered a need. A sundial gave time from sunlight. A water clock gave time by motion in the dark. Together, they widened the human ability to notice and organize the day. Across Egypt, Mesopotamia, Greece, China, India, and other places, No single story explains all water clocks. They arose in many forms, shaped by local materials, customs, questions, and skills. Some measured short intervals, some helped divide the night, some supported courts, temples, observatories, or households. Some were plain and useful, others were beautifully made. And always in the background, there was the sound of water. A drop gathered, a drop fell, a surface rose, or a level sank. In the quiet of a chamber, time became a small movement that could be heard as well as seen. Beyond the walls, the world continued in larger rhythms. Fields waited for their seasons. Markets opened with the morning. Lamps were lit in streets and courtyards. People gathered to speak, to pray, to trade, to plant, and to rest. And somewhere nearby, a vessel of water kept its patient measure, drop by drop, through the soft hours. Chapter 4. Time in Temples, Fields, and Cities. As people learned to read shadows, watch water, and follow the changing sky, timekeeping became more than a private act of noticing. It became something shared. A village, a temple, a city, or a farming community could move more easily when people had some common sense of when to gather, when to begin, and when to wait. In the fields, time was often broad and seasonal. A farmer did not need to know that it was precisely the third hour after sunrise, in the way a modern clock might say it. More important was the soft knowledge of the year, when the rains usually came, when the river might rise, when the soil was ready, when birds returned, when certain stars appeared before dawn, and when the first green shoots pushed through the earth. Agricultural time was measured in warmth and moisture, in seed and harvest, in the color of grain bending under the sun. People watched the sky, but they also watched the ground. They noticed when trees flowered, when fruit ripened, when animals moved through familiar paths. These were all timekeepers too, quiet and living, each one part of a larger pattern. Calendars helped hold these patterns in memory. A calendar is simply a system for organizing days into longer shakes, such as months, seasons, and years. Ancient calendars often drew from several sources at once: the sun, the moon, and the stars. The sun gave the year its seasonal rhythm. The moon, changing shape from night to night, offered a visible cycle of about a month. The stars marked the returning seasons, appearing in certain places in the sky at certain times of year. In some societies, priests, astronomers, scribes, or other official timekeepers watched these patterns carefully. A scribe might record the day on clay, papyrus, wood, bamboo, or parchment. An astronomer might observe the moon's shape, or the rising of a bright star. A temple official might know when a festival should be prepared, when lamps should be lit, when songs or offerings belonged to the season. This kind of timekeeping was practical, but it was also meaningful. It helped people plant and harvest. It guided market days, when goods could be brought from farms and workshops into a town square. It supported legal proceedings, so that disputes, agreements, and public decisions could be heard at appointed times. It helped organize civic life, meaning the life of a town or city, meetings, ceremonies, work duties, and public gatherings. In many places, the day itself was divided differently from the way we divide it now. Some societies used what are called unequal hours. This means that the daylight might be divided into a set number of parts, and the night into another set number of parts, but those parts changed length with the seasons. A daylight hour in summer, when the sun stayed long above the horizon, might be longer than an hour in winter. Could be longer than a daylight hour in winter. Time followed the sky closely, stretching and narrowing with the year. This may seem unusual from the viewpoint of modern clocks, but it was a natural way to live with the sun. The day was not forced into identical pieces. It breathed with the seasons. Morning work, midday rest, evening duties, and nighttime watch all belonged to the changing length of light and darkness. In cities, time became more audible. Before most people owned personal clocks, public signals helped communities know what part of the day had arrived. A drum might sound from a gate or tower. A bell might ring across rooftops. A call might rise from a high place and drift through narrow streets. Chants could mark a sacred hour. These sounds did not need to be exact to the second. They were signals of shared rhythm, reminders that the community was turning together through the day. One might imagine a market beginning in the cool light of morning. Stalls open slowly. Baskets are set down. Cloth is unfolded. Bread, fruit, fish, grain, oil, and pottery find their places in the square. People arrive by habit, by custom, by the angle of the sun, and perhaps by a sound heard from a nearby temple or civic building. The hour is not a number glowing on a face, it is a gathering of signs: light on stone, voices in the street, smoke rising from cooking fires, footsteps becoming more numerous. Religious time also gave shape to daily and yearly life. A ritual is a repeated action with religious or symbolic meaning, and many rituals depend on being done at the proper time. Some observances returned each day, others came with the moon, with the season, or with a particular date in the calendar. Festivals could be tied to harvest, renewal, remembrance, or the turning of the year. In ancient temples, the marking of time could be careful and dignified. The opening of doors, the lighting of lamps, the recitation of words, the preparation of offerings, and the movement of processions might all follow an order shaped by tradition. Timekeeping here was not only measurement. It was a way of placing human action within a larger order, beneath the sun, beneath the moon, beneath the familiar stars. Across the world, many religious traditions developed their own careful ways of marking time. In Islamic societies, the 5 daily prayers are linked to the position of the sun. This made the observation of daylight especially important. Over time, some mosques had specialized timekeepers called muwaqqits. A muwaqqit was a person trained to calculate prayer times, often using astronomy and mathematical knowledge. Their work joined devotion with observation, showing how closely the sky and daily practice could be connected. In Jewish tradition, the Sabbath and many festivals are tied to sunset and to calendar calculation. In Buddhist monasteries and other religious communities, bells, drums, chants, and schedules have long helped order the day. In Christian communities too, prayer might return at regular hours, with bells calling people from work or silence into common observance. Each tradition had its own forms, yet many shared the same gentle idea: time could be honored by returning again and again to certain acts. Civic time and sacred time often overlapped. A bell might call people to prayer, but it might also mark the opening of a gate or the beginning of a meeting. A calendar might guide a festival, but also a tax collection, a court session, or a market. A seasonal observance might remind farmers when to prepare fields or bring in crops. Time belonged not to one part of life, but to many. And still, older rhythms remained close. Even in cities, people noticed the heat of noon, the cooling of evening, the first lamps in doorways, the birds settling along rooflines. Workers followed daylight. Travelers watched weather. Families knew the customary times for meals, chores, visits, and rest. Time was flexible, local, and shared, shaped by place as much as by instrument. As evening settled over an ancient town, the day's measurements softened. Market sounds thinned. A final call might drift over the rooftops. A bell or drum might answer from another quarter. Lamps were lit one by one, small flames trembling in doorways and courtyards. Above them, the moon and stars returned, steady and patient. From these daily rhythms, people also looked toward longer ones. They counted not only the hours of a day, but the days of a month, the months of a season, and the seasons of a year. In time, calendars would become some of humanity's most careful works, records of festivals, harvests, rulers, journeys, and the great returning patterns of the sky. Chapter 5. The Careful Calendars of the Ancient World. A calendar is a quiet kind of map. Instead of showing rivers, roads, and mountains, it shows the paths of days. It gathers mornings and evenings into longer shapes, weeks, months, seasons, and years. It helps people remember when to sow seed, when to expect rain, when to hold a festival, when to begin a journey, and when to look for the return of a familiar star. Long before printed pages hung on walls, calendars lived in careful observation. A person might watch the moon grow from a thin silver curve to a round, bright disk, then fade again into darkness. This lunar cycle, meaning a cycle of the moon, gave many peoples a natural way to count months. Others watched the sun's path through the year, noticing the lengthening and shortening of days, the return of warmth, the arrival of cold, the flowering of plants, and the ripening of grain. This was solar time, time guided by the sun and the seasons. Many calendars tried to hold both together. These are called lunisolar calendars, lunar for the moon, solar for the sun. They follow moon months, but they also make adjustments so that those months do not drift too far away from the seasons. It is a delicate task, like keeping two slow songs in harmony. The reason is simple, though the solutions can be wonderfully intricate. A year is not an exact whole number of days. The moon's months do not fit neatly into the sun's year. Nature is steady, but not arranged in perfect squares and columns. So people learned to add a little time now and then, a leap day, or sometimes a leap month. The older word for this is intercalation, which simply means placing extra time into a calendar so that it stays close to the sky. In ancient Egypt, where the Nile shaped the life of fields and villages, the calendar was closely tied to the seasons of the river and the land. Egyptian observers watched the heavens with patience, including the bright star Sirius, whose first appearance before sunrise was associated with the season of the Nile flood. Alongside sacred and lunar reckonings, Egypt developed a civil calendar of 365 days. It had 12 months of 30 days each, followed by 5 extra days at the end of the year. There is something gentle and orderly in that arrangement. 12 even months, then 5 days set apart, like stones placed after a path. But the original Egyptian civil calendar did not include a regular leap day. Over long spans of time, it slowly shifted against the solar year. Even so, it was useful, elegant, and influential, a careful way to organize administration, labor, offerings, and memory beneath the clear desert sky. Farther east in Mesopotamia, Babylonian astronomers and scribes watched the moon and stars from cities of baked brick and open courtyards. Their calendar was lunisolar. Months began with the moon, but the year was kept near the seasons by adding intercalary months when needed. These extra months helped festivals and agricultural times remain in their proper places. The Babylonians became known for their mathematical astronomy. They recorded observations, recognized patterns, and passed down methods that later influenced Greek astronomy, and, through many channels of learning, Islamic astronomy as well. Their calendar was not merely a list of days. It was part of a larger habit of watching the sky carefully, writing what was seen, and finding order in repeated motion. In China, too, the calendar grew from long attention to both heaven and earth. The traditional Chinese calendar is lunisolar, using months connected with the moon, while also keeping the year aligned with the sun's seasonal course. In some years, a leap month is added. This helps lunar months remain connected to the turning of the agricultural year and to the timing of festivals. A calendar in such a tradition was not only practical, it also carried cultural, ceremonial, and governmental meaning. To announce the calendar was to help set the rhythm of public life. It told communities when to prepare, when to gather, when to honor ancestors, and when to mark renewal. In the quiet image of a written calendar, one can almost see brush marks on silk or paper, and beyond them, fields changing under a wide, pale sky. Across the ocean, in Mesoamerica, the Maya developed some of the most sophisticated calendrical and astronomical systems of the ancient world. Their timekeeping included several interwoven counts. One was a 260-day ritual calendar, used for sacred and ceremonial purposes. Another was the 365-day Hab-A, a solar calendar, organized for the cycle of the year. They also used the long count, a system for recording longer spans of time. Maya scribes and astronomers observed cycles of the moon, Venus, eclipses, and other celestial patterns with great skill. Their calendars were not simple or single-purpose. They formed a layered way of understanding time: ritual time, seasonal time, historical time, and cosmic time. In carved stone, painted books, and temple alignments, time could be counted, remembered, and honored. In Rome, the calendar also changed over centuries. Early Roman timekeeping was adjusted and revised as civic and religious needs shifted. By the 1st century BCE, the calendar had become misaligned enough with the seasons that reform was needed. Julius Caesar introduced the Julian calendar in 45 BCE, drawing on solar reckoning and adding a leap day every 4 years. This was a powerful correction. The Julian calendar gave the year a more regular structure and helped keep dates closer to the seasons. Yet even this was not perfect, because the solar year is a little shorter than the Julian calendar assumed. The difference was small from year to year, but over many centuries, small differences become visible. So, in 1582, under Pope Gregory XIII, another reform was introduced: the Gregorian calendar. It adjusted the leap year rule, leaving out some leap days and century years unless those years met a further rule. This brought the calendar closer to the actual length of the solar year. The Gregorian calendar is now widely used around the world for civil purposes, though many religious and cultural calendars continue alongside it, each carrying its own history and meaning. No calendar is perfect in the sense of being effortless forever. Each is an agreement between human life and the motions of the sky. Each says in its own way, let us keep the planting near the rains, the harvest near the ripening, the feast near its season, and the remembrance near its proper day. There is tenderness in this long work of counting, a mark pressed into clay, a notch cut into wood, a line written on parchment, a page turned at the beginning of a month, a festival lamp lit when the season returns. As calendars guided the great circle of the year, other forms of timekeeping gathered around the smaller circle of the day. In temples, monasteries, mosques, shrines, and homes, people listened for bells, watched candles burn lower, tended lamps, breathed incense, and paused for prayer. The year had its sacred seasons, and the day, too, began to find its gentle hours. Chapter 6: Monasteries, Bells, and the Hours of Prayer. As the long centuries turned from the ancient world toward the Middle Ages, time was still often measured by light, shadow, water, and the familiar changes of the sky. Yet in many communities, another kind of time became important too. A time of repeated devotion, marked not only by the sun's path, but by voices, bells, candles, and quiet footsteps along stone corridors. In medieval Christian monasteries, daily life was shaped by what were called the canonical hours. These were regular times set aside for prayer. They did not always match the fixed hours on a modern clock. Their timing could vary with season, location, and the customs of a particular monastery. But they gave the day a gentle structure, like stones set one after another, across a stream. There was matins, or vigils, often kept in the deep quiet before dawn. There was lauds, a service of morning praise as light began to gather. Prime came early in the day, followed by terce, sext, and none, names that came from older ways of counting daylight hours. Vespers belonged to evening, when the day softened and lamps were lit. Compline came at the close, a final prayer before the community entered the stillness of night. In a monastery, these hours were not only ideas written in a book. They were heard and felt. A bell might sound through mist before sunrise, its note moving slowly across gardens, roofs, and fields. Sandaled feet might pass along a cloister, a covered walkway surrounding a quiet courtyard. Pages might turn in a chapel by candlelight. Voices might rise together and chant, then settle again into silence. The bell was one of the most important timekeepers of monastic life. It called people to prayer, but also to work, meals, study, and rest. Before personal clocks were common, sound carried time from one person to another. A bell did not place a small dial in every hand. Instead, it gathered the community into a shared rhythm. Those who heard it knew that one part of the day had ended and another had begun. This regular pattern encouraged more careful daily timekeeping in medieval Europe. Monasteries did not invent timekeeping, and they did not create all later clocks by themselves. But their need for repeated observances helped foster attention to the hours. Someone had to notice the sky, tend the lamps, watch the passage of the night, and know when to ring the bell. Time in such places was both practical and spiritual. It ordered the baking of bread and the copying of manuscripts, the tending of gardens, and the singing of psalms. Religious timekeeping was not limited to Christian monasteries. Across the world, many traditions marked sacred time with equal care. In Islamic communities, the 5 daily prayers are linked to the sun's position, from the first light of dawn through midday, afternoon, sunset, and night. Over time, specialists known as muwaqqits helped calculate prayer times for mosques, using astronomy, mathematics, and close observation of the heavens. In Jewish practice, time has long been tied to sunset, the calendar, and the turning of weeks and festivals. The Sabbath begins at evening, as one day gives way to the next. Festival dates depend on careful calendar reckoning, keeping sacred observances connected with the proper season. Here, too, time was not merely counted. It was received, remembered, and honored. In Buddhist monasteries and in other religious communities, bells, drums, wooden clappers, chants, and daily schedules marked the movement of hours. A bell might signal meditation. A drum might announce a gathering. Incense might rise in a pale blue thread, while the air held the faint fragrance of sandalwood or aloes wood. In many places, sound and scent became companions to time. Alongside bells and sky watching, people used quieter devices to follow the passing hours. A candle clock measured time by the burning down of a marked candle. As the flame slowly consumed the wax, markings along the side could show how much time had passed. There is a famous story that King Alfred of England used carefully measured candles to divide his day, though historians are not certain how much of that story is true. Still, the idea itself is simple and graceful, a small flame giving shape to darkness. Marked oil lamps worked in a similar way. As the oil burned lower, markings on the vessel could suggest the passage of time. These lamps were not perfectly precise instruments. The flame could change with the quality of the oil, the wick, and the movement of air. But in a dim room, they offered a gentle guide, a visible measure of the night's quiet progress. In parts of East Asia, especially China and later Japan, incense clocks were used. An incense clock measured time by the steady burning of incense. Some were simple trails of powdered incense laid in patterns. Others were more elaborate, with different scents marking different intervals. As the incense burned, it left behind a delicate line of ash, and time became something one could almost smell in the air. These forms of timekeeping remind us that accuracy was not always the only purpose. A candle, a lamp, a bell, or a line of incense could help a community keep order, but they also shaped the feeling of the day. They made time visible, audible, fragrant, and shared. Prayer hours often shifted with the seasons. In summer, daylight stretched long into evening. In winter, darkness gathered early. Some systems divided the daylight into portions, so an hour of daylight might be longer in summer and shorter in winter. This was different from the equal hours of a modern clock, but it made sense in a world still closely guided by the sun. And so, through monasteries, mosques, synagogues, temples, and quiet homes, time continued to be kept in many ways. It was calculated by scholars, watched by attendants, sung by communities, and carried by bells through the open air. It lived in the lowering lamp, the curling incense, the first light before dawn, and the hush after evening prayer. As centuries passed, the bell's voice would remain, but gradually, in some towns, bells began to be joined by hidden machinery. High in towers, weights would descend, gears would turn, and a new kind of clock would begin to measure the hours with iron teeth and patient motion. For now, the sound lingers softly over stone walls and darkening fields, one calm note fading into the next. Chapter 7. The First Mechanical Clocks. By the late 13th and early 14th centuries, in parts of Europe, a new kind of timekeeper began to appear in high, echoing places. It did not depend on sunlight falling across a courtyard. It did not depend on water dripping from one vessel to another, on a candle burning lower by degrees, or on incense leaving a thin line of fragrant ash. This new timekeeper was made of moving parts, weights, wheels, teeth, and levers, arranged with patient care inside towers and church buildings. These were the first mechanical clocks of medieval Europe. It is best not to imagine a single clear beginning, as though one clock suddenly appeared and all the older ways were forgotten. The change was slower than that. Many early clocks have been repaired, rebuilt, or altered over the centuries, so historians are careful about saying which one came first. What we can say is that, around this period, large clocks driven by machinery began to mark time in monasteries, cathedrals, town halls, and clock towers. They were not usually personal possessions. They were not tucked into pockets, placed on small tables, or carried from room to room. They belonged to communities. A town might hear one. A monastery might organize its hours around one. A cathedral might keep one within its stone walls, where the air was cool, and the sound of turning parts was softened by distance. Inside such a clock, the power often came from a falling weight. A heavy weight, suspended on a rope or chain, slowly descended under the pull of gravity. Gravity is the same steady force that makes rain move down a window pane. In a clock, this downward pull gave energy to the mechanism. If the weight were allowed to drop freely, it would fall too quickly, and all its energy would be spent at once. So the clock needed a way to let that energy out little by little. This is where one of the most important parts appeared, the escapement. An escapement is a device that releases motion in small, regular steps. A simple way to picture it, is as a careful gate. Instead of letting everything rush through at once, the gate opens and closes, allowing just a little movement each time. In a mechanical clock, this steady release helped the gears turn in measured intervals. The gears were toothed wheels. One wheel turned another. One part passed motion to the next. Slowly, steadily, the weight descended. Slowly, steadily, the wheels moved. And somewhere in the tower, a hammer might be lifted and released, striking a bell. Many early mechanical clocks did not show the time on a face, as modern clocks do. They did not always have a dial with hands. Often their most important purpose was to sound the hours. A bell could be heard by many people at once. It could drift over roofs, through market streets, across cloisters, and into nearby fields. In this way, time became something shared through sound. A person might not see the clock at all. A worker in a lane, a monk in a garden, a merchant arranging cloth in a stall, or a traveler stepping through a gate, might simply hear the bell. The hour was not yet a private number glowing on a screen, nor a quiet watch face on the wrist. It was a public note in the air. The clocks themselves were not perfect by modern standards. They could gain or lose time. Their parts needed care. Temperature, wear, friction, and craftsmanship all mattered. But even with their limits, they brought a new regularity to civic life. Civic means related to the life of a town or city. Public clocks helped people gather, work, pray, trade, and meet, with a little more agreement than before. Older rhythms continued alongside them. The sun still rose over the fields. The seasons still guided planting and harvest. Bells still called people to prayer. Market days still followed calendars shaped by custom and festival. Mechanical clocks did not erase these things. They joined them. In some places, clocks became wonderfully elaborate. Astronomical clocks, which show information about the heavens as well as time, appeared in important churches and cities. Famous examples are associated with Strasbourg, Prague, Wells Cathedral, and the Salisbury Cathedral area, though claims about the oldest surviving or working clocks must be handled with care. Over many centuries, clocks were changed, restored, or rebuilt, and their histories can be layered like old stone walls. An astronomical clock might show the motion of the sun or moon, the signs of the zodiac, or the turning of the calendar. Such clocks remind us that mechanical time did not grow apart from sky time all at once. Even as gears turned in towers, people still wanted to understand the heavens. The machinery inside the clock echoed the great movements above, the daily path of the sun, the changing moon, the circling stars. Gradually, clock faces with hands became more common. A hand moving over a dial made time visible as well as audible. Yet in many towns, the bell remained the most familiar voice of the clock. Its sound could cross distances that a clock face could not. Imagine a medieval town in the late afternoon. The streets are narrow and quieting. Smoke rises lightly from hearths. The stones of the church tower hold the warmth of the day, while shadows gather in doorways and under eaves. High inside the tower, a weight descends by a small measure. A gear turns, another gear answers. The escapement allows one step, then another, in its careful rhythm. Then the bell sounds. The note rolls outward, softening as it travels. It passes over tiled roofs, over a small square, over carts standing near the market, over pigeons settling along a ledge. People hear it without needing to look up. For a moment, the town is gently gathered into the same hour. And beyond the town walls, evening continues to widen. Roads lead toward rivers lead toward harbors. In the distance, ships wait with folded sails and lanterns ready. Above them, the first stars begin to appear, quiet and patient, over the open sea. Chapter 8. Time at Sea. Sandglasses, Stars, and Longitude. Out on the open sea, time had a different feeling. There were no town towers rising above rooftops, no courtyard sundials resting in familiar light, no monastery bells carried across fields. There was only the wide water, the turning sky, the wind moving through rigging, and the slow lift and fall of the ship beneath the feet. For sailors, time was not only a way to mark the day, it was a way to find a path. A ship crossing the ocean needed many kinds of knowledge. Sailors watched the stars. They observed the sun. They used the compass, which pointed toward magnetic north. They read charts, listened to the wind, studied currents, and measured the ship's motion through the water. Timekeeping became part of this quiet art of navigation, woven into the whole practice like a line carefully tied into a sail. On board, one of the simplest timekeepers was the sandglass. A sandglass, or hourglass, measures time by letting fine sand pass through a narrow opening from one glass bulb into another. At sea, smaller glasses were often more useful than large ones. A common shipboard glass measured half an hour. When the sand had run through, someone turned it over, and the time began again. The sound was almost nothing, just a faint whisper of grains falling in the lantern-lit dimness, while outside the hull, the sea moved in long, dark swells. These half-hour glasses helped mark the ship's watches. A watch was a period of duty, when part of the crew stayed alert to steer, trim sails, keep lookout, and tend the needs of the vessel. Bells were rung as the glass was turned, creating a shared rhythm through the day and night. One bell, then another, until the watch was complete, and the next group of sailors took their place beneath the sky. The sandglass was useful because it was simple and portable. It did not require sunlight like a sundial. It did not depend on a still floor, like some delicate instruments. It could be carried, turned, and used again. Yet it was not perfect. Damp air, uneven sand, rough seas, and human attention could all affect its accuracy. Still, for many shipboard tasks, it was a faithful companion. There were other practical measures as well. Sailors used a log and line to estimate the ship's speed. A piece of wood, the log, was thrown overboard, attached to a line with knots tied at regular intervals. As the ship moved away from the floating log, the line ran out. By counting how many knots passed during a measured time, sailors could estimate speed. Above, the sky offered older guidance. Finding latitude, the north-south position on Earth, was often more manageable than finding longitude. Latitude could be estimated by measuring the height of the sun at noon, or the height of certain stars above the horizon. In the northern hemisphere, the pole star gave a steady clue, resting near the north celestial pole. The higher it appeared, the farther north a sailor was. Longitude, the east-west position, was more difficult. The Earth turned steadily, carrying places into sunrise and sunset, one after another. If a sailor knew the time at a reference place, such as a home port or an observatory, and also knew the local time on the ship, the difference between those times could reveal how far east or west the ship had traveled. In simple terms, longitude was a question of comparing two clocks, the time where you were, and the time at a known place far away. But keeping a reliable clock at sea was not easy. A ship is never truly still. It rises, dips, rolls, and leans. Salt air enters small openings, temperatures change, wood swells, metal responds to warmth and cold. Early mechanical clocks, already imperfect on land, struggled even more aboard a vessel. For long ocean voyages, losing track of longitude could mean uncertainty over distance from shore, hidden reefs, or the proper course across wide waters. This became known as the longitude problem. It was not a puzzle for one person alone, but a broad and practical challenge involving astronomers, mathematicians, instrument makers, navigators, and governments. In 1714, Britain passed the Longitude Act, offering rewards for methods that could determine longitude accurately at sea. The need was clear, and the solution would come through more than one path. One important method used the moon. The moon moves across the background of stars in a predictable way. By measuring the angle between the moon and certain stars or the sun, and comparing the observation with published tables, navigators could work out the time at a reference location. This was called the lunar distance method. It required careful observation and calculation, and it became a useful part of navigation, especially before marine chronometers were widely available. Another path was the making of a clock steady enough to carry reference time across the sea. This is where John Harrison enters the story. Harrison was an English carpenter and clockmaker in the 18th century. He was not alone in the larger effort to improve navigation, but his work became especially important. With patience and remarkable skill, he designed marine timekeepers that could endure the motion and changing conditions of a ship far better than earlier clocks. His first sea clocks were large and ingenious. Over many years, he refined his ideas, learning from each design. Eventually, he produced H4, a large watch-like chronometer. A chronometer is a very accurate timekeeper, and H4 was tested in the 1760s with notable success. It looked much more like an oversized pocket watch than a tower clock or a household clock. Yet inside it held the careful work of long observation, adjustment, and craft. A marine chronometer allowed sailors to carry the time of a known reference place with them. Imagine a ship leaving port with its chronometer set to the time at Greenwich or another chosen location. Each day at sea, the navigator could determine local noon by observing the sun. By comparing the ship's local time with the chronometer's reference time, the ship's longitude could be calculated. The clock, resting carefully in its box, became a quiet link between the moving vessel and a fixed point on land. At first, such chronometers were expensive and uncommon. They did not appear on every ship at once. Like many forms of timekeeping, they spread gradually, becoming more reliable, more available, and more deeply woven into practice over time. Navigators continue to use several methods together: stars, sun, compass, charts, lunar distances, estimates of speed and direction, and increasingly, chronometers. The sea encouraged humility. No single instrument removed the need for judgment. A good navigator gathered many signs, checked them against one another, and moved carefully through uncertainty. Still, the improvement in marine timekeeping changed ocean travel. It helped ships cross long distances with greater confidence. It helped mapmakers refine coastlines and routes. It connected distant shores through a more dependable understanding of where a ship lay beneath the wide sky. And yet, in the quiet of a night watch, the scene could remain very simple. A lantern swayed softly in the cabin. A sandglass waited to be turned. Above deck, stars appeared clear and patient between slow-moving clouds. Somewhere below, a chronometer rested in its padded box, keeping the time of a far-off meridian. The ship moved onward through dark water, guided by wind, mathematics, memory, and the steady human wish to know one's place. Time at sea was both practical and poetic. It lived in the falling sand, the ringing bell, the measured height of a star, and the tiny beat of a careful machine. And as the story of timekeeping drifted back toward land, it found rooms more still than any ship could be. There, away from the rolling swell, the hanging weight could swing evenly from side to side, and the age of the pendulum would begin. Chapter 9: Pendulums and the Age of Precision. In the long history of timekeeping, there is a quiet moment when time seems to begin swinging gently back and forth. Left, right. Tick, pause. Swing, return. A pendulum is a simple thing to picture. It is a weight hanging from a fixed point, free to move in a smooth arc. A stone tied to a cord can be a pendulum. So can a metal bob suspended from a rod inside a clock case. If it is set in motion, it travels to one side, slows, turns, and comes back again. Under the right conditions, this motion can be remarkably regular. That regularity made the pendulum one of the great gifts to clockmaking. Long before pendulum clocks appeared in homes and observatories, people had watched swinging objects with curiosity. One of the most famous stories belongs to Galileo Galilei, the Italian thinker who studied motion, astronomy, and mathematics in the late 16th and early 17th centuries. Tradition says that as a young man, Galileo watched a lamp swinging in Pisa Cathedral and noticed that each swing seemed to take nearly the same amount of time, even as the arc grew smaller. The story is well known and pleasing to imagine. A high-vaulted church, a lamp moving slowly in the air, a young observer counting its motion by the beat of his pulse. Yet, like many old stories, it is not certain in every detail. What matters is that Galileo did study pendulum motion carefully. He understood that the swing of a pendulum could be used to measure time more evenly than many older methods. He did not build the first successful pendulum clock, but his studies helped prepare the way. The person who made that next step was Christian Huygens, a Dutch mathematician, astronomer, and inventor. In 1656, Huygens built and patented the first successful pendulum clock. A patent is a kind of official protection for an invention. Recognizing the maker's design. Huygens' clock used a pendulum to regulate the movement of gears, helping the clock divide time into much steadier portions than many earlier mechanical clocks had done. Before pendulums, mechanical clocks were useful, impressive, and important, but they could drift. They had weights, gears, and escapements, the small regulating parts that allowed energy to be released step by step. But their steps were not always even. Friction, temperature, and imperfect workmanship could all affect them. A pendulum brought a new calmness to the mechanism. Its swing gave the clock a more dependable rhythm. Left, right, tick, pause, parts wore down. But the pendulum gave clockmakers a steady partner, a repeating motion that could be refined with patient craft. This new precision was useful in many quiet places. In observatories, where astronomers watched the heavens, more accurate clocks helped record the movements of stars and planets. A star might cross a marked line in a telescope's view, and the observer could note the time. Over many nights, such notes became patterns, and patterns became knowledge. Timekeeping and astronomy had always been companions beneath the sky, and the pendulum strengthened that old companionship. In scientific experiments, better clocks helped measure motion, falling objects, flowing liquids, and many small changes that required careful timing. In workshops, clocks supported the regular rhythms of skilled labor. Artisans could compare, test, and adjust their instruments more finely. In some homes, clocks became part of domestic life, no longer only distant bells from a tower, but a steady presence in a hall or sitting room. One familiar form was the long case clock, often called a grandfather clock. These tall clocks became more common in some households from the late 17th century onward. Their height gave room for a long pendulum to swing inside the wooden case. The case might be polished oak, walnut, or another warm wood, standing quietly against a wall. Behind the door, weights hung from cords or chains. The pendulum moved in its narrow space, left and right, while the dial above showed the hours and later often the minutes as well. To stand near such a clock was to feel time not as a bell over rooftops, but as a soft, repeated sound within the room. The tick was not hurried, it was measured and patient. It belonged to the house as much as the table, the hearth, or the window where moonlight rested on the floor. Pendulums, however, preferred stillness. They worked best in stable, stationary places, where the floor did not roll and pitch beneath them. At sea, a ship's movement disturbed the pendulum's swing. The deck lifted, dipped, and leaned with every swell. For navigation on the ocean, other kinds of timekeepers were needed, especially marine chronometers designed to keep steady time despite motion. So the pendulum became most at home on land, in observatories, towers, workshops, and quiet rooms. The 17th century also brought improvements to watches. Watches had existed before, powered by springs rather than hanging weights, but early ones were often not very accurate. A spring stores energy when it is wound, then releases it as it unwinds. To make a watch keep better time, it needed a regulating part small enough to carry. The balance spring, developed in the 17th century, helped solve this. It is a tiny spring that controls the back-and-forth motion of a balance wheel, rather like a small, portable cousin to the pendulum's steady swing. With balance springs, watches gradually became more reliable, though fine watches remained costly and took skilled hands to make. Still, the pendulum clock had a special place in the age of precision. It showed that time could be divided more evenly, not only by the sun's shadow, by dripping water, or by the burning of candles, but by motion itself. A simple swing could guide wheels and hands. A repeated arc could turn into seconds. A weight returning again and again could help people read the heavens, measure experiments, and order the hours of daily life. And yet, even with this new accuracy, time did not lose its older meanings. The clock might tick in the corner, but dawn still came slowly over fields and rooftops. The moon still changed its shape, night by night. Seasons still opened and closed in their own broad rhythm. The pendulum did not replace the sky, it simply added another way of listening. In a quiet room, the clock stood patiently. Its polished wood held the faint scent of oil, dust, and age. Brass weights rested inside, descending so slowly that their motion could barely be seen. The pendulum moved in shadow, left, right, tick, pause, swing, return. Beyond the window, the world settled into evening. A clock face caught a little moonlight. Somewhere, a watch lay closed in a drawer, waiting to be carried. In time, smaller personal timekeepers would travel in pockets, and public clocks would look down over railway platforms, helping whole regions agree on the hour. But for now, In the stillness of the house, the pendulum kept its gentle measure, and the night moved on around it. Chapter 10. Pocket watches, railways, and shared time. For many centuries, time was something people mostly met in common. It sounded from a tower bell, appeared in the shadow on a wall, or moved quietly in the hands of a household clock. A village might know the hour by the church bell. A city might look toward a public clock above a market square. In a home where a clock stood in the hall, its ticking belonged to everyone who lived there. But slowly, time began to travel in pockets. Around the 15th century in Europe, makers began creating small, portable clocks powered by springs. A spring could be wound tightly, storing energy in a compact space. As it unwound, it could move the wheels of a little clock. These early portable timekeepers were not yet the neat, accurate watches of later centuries. They might be worn as pendants or carried carefully. They were often expensive, delicate, and as much objects of craftsmanship as practical tools. Still, something important had begun. Time was no longer only in towers or on walls. It could be held in the hand. From the 16th and 17th centuries onward, pocket watches became more common, especially among people with wealth enough to afford them. A watch might rest in a small case of brass, silver, or gold. It might be tucked into a waistcoat pocket, attached to a chain, and drawn out with a quiet, familiar motion. Its face, protected under glass, offered a private glance at the hour. At first, these watches were not always very precise. Like all small machines, they depended on careful making, clean parts, steady regulation, and gentle use. But watchmakers kept refining them. One important improvement was the balance spring, developed in the 17th century. A balance spring is a tiny spring that helps regulate the movement of a watch, a little like the pendulum in a standing clock, but small enough for a portable timekeeper. It gave watches a steadier rhythm, helping them become more accurate. In time, pocket watches became practical companions for merchants, travelers, officials, and skilled workers. They remained costly for a long while, and many people still lived by public clocks, bells, daylight, and habit. Yet the idea of personal timekeeping continued to spread. A person could carry an hour with them across a field, through a busy street, or onto a road leading out of town. As workshops grew and cities became larger, clock time became more present in daily life. Industrialization, the great change toward machine production and urban work, brought more people into factories, offices, and scheduled labor. The day, once shaped mainly by daylight, weather, and seasonal tasks, was increasingly divided by bells, shifts, appointments, and wages counted by the hour. This did not happen all at once, and it was not felt in the same way everywhere. Older rhythms continued. In cities, the clock became a stronger companion. Timekeeping helped people coordinate work and trade, but it also changed habits. It made the day feel more measured. It encouraged punctuality, arriving at the agreed moment, not simply sometime in the morning or before evening. Then came the railways, stretching their iron lines across landscapes. At first, each town often kept its own local solar time. Local solar time means time based on the sun's position in that particular place. When the sun reached its highest point in the sky, it was noon there, but noon in one town might be several minutes different from noon in another town to the east or west. When travel was slow, such differences mattered little. A carriage or a walking traveler did not need a timetable to the minute. Trains changed this gently but firmly. A train leaving one town and arriving in another needed a shared schedule. Conductors, station masters, passengers, and signalmen all needed to agree on what the printed hour meant. If every station used its own local time, even a few minutes' difference could cause confusion. So railway time began to bring places into agreement. In Britain, railways widely adopted Greenwich Mean Time during the 19th century. Greenwich Mean Time, or GMT, is time based on the prime meridian at Greenwich, in London. A prime meridian is a chosen zero line for measuring longitude, the east-west position of places on Earth. Greenwich had long been important in navigation and astronomy, and its observatory provided a steady reference. Railway clocks were adjusted to this shared time. A station clock under a glass face, glowing in lamplight, could tell the same time as another station far down the line. Timetables became clearer. Journeys could be planned with greater confidence. In Britain, Greenwich Mean Time became legal standard time in 1880. Standard time means an agreed time used across a region. It is a social agreement as much as a scientific one. People decide that, for the sake of coordination, A large area will keep one clock time together, even though the sun may stand a little differently in each town. Across North America, where distances were vast and railway lines crossed many regions, the need was even more noticeable. In 1883, North American railroads adopted standard time zones. A time zone is an area that uses the same standard time. Instead of every town following its own solar noon, broad regions shared a common hour, making railway schedules easier to read and follow. The following year, in 1884, representatives from many nations met at the International Meridian Conference in Washington, D.C. There they selected Greenwich as the prime meridian for international reference. This did not make the whole world change its clocks overnight. Time zones were adopted gradually and irregularly. Local law, politics, commerce, geography, and convenience all shaped the map of time. Even now, time zones do not fall in perfectly straight lines. They bend around borders, islands, regions, and human choices. Still, the railway age helped make time more widely shared. A traveler could stand on a platform at dusk, holding a folded timetable, and look up at the station clock. Steam might drift softly beneath the roof. Lamps might glow along the carriages. Somewhere down the track, another clock showed the same agreed hour. The pocket watch had made time personal. The railway clock made it coordinated across distance. And as signals moved along the rails, as schedules passed from town to town, timekeeping was already preparing to become quieter still. Beyond the visible hands of station clocks, a new precision would begin to hum in wires, crystals, laboratories, and one day, in satellites circling silently above the night side of Earth. Chapter 11. Quartz, Atomic Clocks, and Invisible Precision. By the 20th century, timekeeping had grown quieter. The great tower bells still rang in many towns. Pendulum clocks still stood in halls and observatories. Pocket watches and wristwatches still carried their small, familiar faces through the day. Yet a new kind of time was beginning to form behind the scenes. Not in the swing of a weight or the turn of a visible wheel, but in tiny vibrations, electrical signals, and careful measurements almost too small to imagine. One of the first great changes came from a clear mineral called quartz. Quartz is a crystal, and a crystal has an orderly inner structure. Its parts are arranged in a repeating pattern, like a very small and very regular lattice. When electricity is passed through a piece of quartz, shaped in the right way, the crystal vibrates. It moves back and forth extremely quickly and steadily. In this way, quartz can be thought of as a tiny crystal tuning fork. Just as a tuning fork gives a steady musical note, a quartz crystal gives a steady electrical rhythm. A clock can count that rhythm. Instead of relying on a pendulum swinging in the air, or a balance wheel turning in a mechanical watch, a quartz clock uses the crystal's vibration as its guide. The vibrations are divided into seconds, minutes, and hours by electronic circuits. The result is a clock that can be much more accurate than most older mechanical clocks. Though quartz clocks, too, can drift depending on temperature and quality. The first quartz clock was built in 1927 by Warren Marrison and J.W. Horton at Bell Telephone Laboratories in the United States. Bell Labs was a place where many researchers worked on sound, electricity, communication, and measurement. Their quartz clock was not a small household object at first. It was a laboratory instrument, carefully made and carefully watched, part of a growing world of radio signals, telephone networks, and scientific timing. Over time, quartz timekeeping became smaller, simpler, and less costly. What had once belonged to laboratories and technical systems gradually entered ordinary rooms, kitchens, offices, and wrists. Quartz clocks did not need winding. Quartz watches could be made thin and light. They kept time well through the small movements of daily life. A notable turning point came in 1969 when the Seiko Astron was introduced in Japan. It was one of the first commercially significant quartz wristwatches. At first, such watches were expensive, but the path had opened. In the years that followed, quartz watches became common around the world. A person could carry for a modest price a timekeeper more accurate than many fine mechanical watches of earlier generations. And so, time became quieter still. A quartz watch might tick so softly that it could barely be heard. A digital clock might glow without any moving hands at all. Time appeared on oven displays, radios, office walls, school corridors, and later on computer screens and small phones. The old craft of springs and gears did not disappear. It remained beautiful and valued. But much everyday timekeeping had slipped into circuits, into small pulses of electricity, into the steady, hidden trembling of a crystal. Beyond quartz, another kind of precision was being developed, even finer and more subtle. Atomic clocks measure time by observing regular behavior inside atoms. An atom is one of the tiny building blocks of matter. It is far too small to see with ordinary eyes, yet its inner patterns can be measured with great care. In an atomic clock, scientists do not watch hands move around a dial. They measure a very steady frequency, or repeated rate, connected with changes inside atoms. A frequency is simply how often something repeats. A swinging pendulum has a frequency. A vibrating quartz crystal has a frequency. Light and radio waves have frequencies too. In an atomic clock, the repeated pattern is extraordinarily stable. The first practical cesium atomic clock was built in 1955 at the National Physical Laboratory in the United Kingdom by Louis Essen and Jack Perry. Cesium is a soft, silvery metal, and cesium-133 is a particular kind of cesio-atom. Its behavior proved so steady that it became central to the modern definition of the second. Since 1967, the SI second, the official scientific second, has been defined using cesium-133. 1 second is counted by 9,192,631,770 cycles of radiation associated with a particular transition in the cesium-133 atom. The number is long, but the idea can be kept simple. Scientists chose a very steady atomic rhythm and agreed to use it as the foundation for measuring time. An atomic clock is sometimes described as listening to an atom's extremely steady note. Even so, atomic clocks are not magical, and they are not perfect in an absolute sense. They are extraordinarily precise, but they are still built, compared, maintained, and corrected by people. Laboratories around the world keep atomic clocks and compare their results. National and international time standards are formed by bringing these measurements together, patiently and carefully, like many quiet voices joining into one calm agreement. This shared time supports much of modern life, often without being noticed. Satellite navigation systems, including GPS, depend on very accurate time. GPS satellites carry atomic clocks as they circle high above Earth. A receiver on the ground, such as the one in a phone or navigation device, compares signals from several satellites. Because radio signals travel at the speed of light, even a very small timing difference can mean a large difference in position. To find a location accurately, the timing must be precise. There is another gentle surprise here. GPS clocks must also account for relativity, the set of ideas developed by Albert Einstein about space, time, motion, and gravity. Clocks high above Earth and moving quickly do not keep time in exactly the same way as clocks on the ground. The difference is tiny, but for satellite navigation, it matters. So the system includes corrections, allowing the signals to remain useful and coordinated. Atomic clocks also help telecommunications, where networks must pass signals in careful order. They support scientific research, where tiny intervals may need to be measured. They help internet systems, financial networks, national laboratories, and international time services. Much of this precision hums quietly in the background. A message is sent, a call is connected, a map finds a road, a computer records an event, and somewhere behind it all, time has been measured with astonishing care. Modern civil time is often coordinated through UTC, or Coordinated Universal Time. UTC is the main world time standard, used as a reference across countries, networks, and scientific work. It is based on atomic time, but it is also kept close to Earth's rotation. Earth does not turn with perfect regularity, its spin varies slightly. Because of this, leap seconds have sometimes been added, 1 second at a time, to keep clock time near the time told by the turning planet. It is a quiet reminder that even in the age of atoms, Earth remains part of the story. The old sky has not gone away. The sun still rises and lowers. The moon still changes its shape night by night. The seasons still arrive in their gradual order. Beneath these ancient rhythms, modern time moves through crystals, laboratories, satellites, and invisible signals. It passes through watches and phones, through cables under streets, and radio waves crossing the air. And then, gently, the great precision softens at the edges. The satellite clocks continue their far circles above the dark side of Earth. The laboratory instruments remain in their cool rooms. The small quartz crystal keeps its steady vibration. Yet close at hand there are older rhythms too, the pulse in the wrist, the easy rise and fall of breathing, the body's own quiet timing beneath the skin. After all the counting, all the signals, all the careful agreement of seconds, time is still something felt as well as measured. It is in the dimming of a room, the hush between sounds, the slow movement of night air, and the stars continuing overhead, as they have done since the beginning of human watching. Chapter 12. Returning to Natural Time. And so, after the long journey through shadows and water, bells and gears, pendulums and crystals, clocks have become almost weightless around us. They no longer need to stand in towers or rest in polished wooden cases. They glow softly on phones, keep order inside computers, travel in satellites high above the earth, and move through quiet networks of signals. They live in watches, ovens, radios, cars, and household devices that remember the hour without asking to be noticed. Much of modern time is invisible. It passes through cables and air, through small circuits and distant clocks kept with extraordinary care. A message finds its way across the world. A train leaves by a printed schedule. A satellite sends a signal from far overhead. Somewhere, a computer compares one tiny interval with another, and the world agrees, gently and silently, on what time it is. Yet beneath all this precision, older rhythms remain. Morning still arrives by light. Evening still gathers by shadow. The year still turns through greening, flowering, ripening, and rest. The moon still changes its shape night by night, as it did for the first watchers who looked upward long before there were written calendars or measured hours. And within each person, time continues in quiet, living patterns. There is the steady rhythm of breathing, rising and falling without needing a dial. There is the heartbeat, patient and continuous. There is hunger returning, energy changing, attention brightening and softening through the day. There is waking and resting, movement and stillness, all part of the body's own way of keeping time. Scientists sometimes call these patterns biological rhythms. A biological rhythm is simply a repeating pattern inside a living thing. One of the best known is the circadian rhythm. Circadian means roughly about a day, and it describes a cycle of about 24 hours. It helps guide many parts of life, when the body tends to feel alert, when it begins to grow quiet, when warmth, hormones, digestion, and rest follow their daily courses. This inner timing is strongly influenced by light and darkness. Morning light helps the body understand that a new day has begun. It is like a soft signal from the sky, passing through the eyes and into the body's deeper clocks. In the evening, dimness and darkness help the body prepare for quiet. The bright world lowers its voice. Lamps may glow more gently. The air may cool. Shadows settle into corners. These rhythms are not exactly the same for everyone. They vary with age, with work, with health, with seasons, and with the amount of light a person receives. Some people feel clear and awake early in the day. Others come slowly into their brightness. Some lives follow regular hours, while others move through changing schedules. The body is not a machine with one fixed setting. It is living, responsive, and always adjusting. Modern clock time and natural time coexist. One does not fully replace the other. A phone may show the hour with perfect confidence, while outside the window, the sky tells its own quieter story. A calendar may name the date, while the first cold scent of autumn says something older. A satellite may keep time from orbit, while the tide draws inward along the shore, pauses, and turns again. In this way, the history of timekeeping has not moved away from nature as much as it has circled around it. The first clocks were the sun and moon, the turning stars, the return of birds, the swelling rivers, the ripening fields. Later came shadows on stone, water in bowls, lamps burning lower, bells in mist, gears in towers, watches in pockets, pendulums in quiet rooms, trains under station clocks, quartz crystals humming almost silently, and atoms giving their tiny, steady note. Each invention brought a new kind of agreement. Each one helped people meet, pray, plant, sail, study, trade, travel, and speak across distance. But behind every measured second, there is still the earth turning. Behind every schedule, there is still dawn. Behind every clock face, there is still the deep pattern of light and dark. Now the precise clocks continue their quiet work. A watch rests on a table, a computer dims, a phone is set aside, its bright face fading to black. Beyond the glass, curtains move softly in the night air. Moonlight lies pale across the floor, not measuring itself, only being present. The breath becomes even, the heart keeps its gentle count. Somewhere beyond the walls, wind moves through leaves, or a distant tide folds itself along the shore. The old timekeepers are still here. Air, water, darkness, stars. Above, the sky remains wide and patient. The same sky that guided the first observers still arches over cities, fields, deserts, mountains, and sea. Its lights appear one by one, calm and far away. And time continues, not hurrying, not stopping, but moving quietly on.